Welcome to today's CCR lesson on linear regression, or lines of best fit. Let's start with some review on scatter plots. Graphing the relationship between two variables to create a scatter plot can help us to draw some conclusions about that relationship. For example, we can decide whether the relationship is a linear one if the plots follow a trend line. For example, these follow a linear shape, so this would be linear. This also follows a linear shape, so this would be linear. However, this is a curve, so we would say this is nonlinear. And this one has no association, so it's also nonlinear. If our scatter plot shows a linear relationship, we can describe that relationship using correlation. For this one, this has a positive correlation, because the dots go up from left to right with a positive slope. As one increases, the other also increases. This one has a negative correlation. As the x values increase, the y values decrease. The slope has a negative, the slope is negative here. This one is nonlinear, so it's not appropriate to use correlation for that. For this one, we could just say no correlation. There's no trend because the dots are all spread out, so we just say no correlation there. So let's take that information and expand upon it into linear regression, or what you might have heard called line of best fit. In real life, our data rarely falls along perfect straight lines. The data shows the relationship between temperature and sunglass sales. Let's start with the correlation, and let's interpret it in the context of the problem. Right now, do you think that this correlation is positive, negative, or no correlation? You should have said here that the correlation is positive. If we interpret that in the context of the situation, what happens to sunglass sales as the temperature increases? You should have said that as temperature increases, the sunglass sales also increase. To make predictions using our data, we can create a line of regression or a line of best fit to represent the data. To estimate this without technology, we can draw a line through the points where about half the points fall above the line and about half fall below the line. However, since the correlation is positive, our line of best fit should have a positive slope. This red line would not be an appropriate line of best fit. Even though it cuts through approximately the center of the points, it does not follow the correct slope. The slope of this line should be positive, and it's negative. This line is a little better. It has a positive slope. It's following the trend of the data, but all the points fall below the line. All the points fall below the line. We want about half of our points to be above the line. This line also has a positive slope, but is also not a line of best fit. Why? You should have said that all the points fall above the line, so this line does not cut through the middle of the points. It is not a line of best fit because all the points fall above the line. This line also has a positive slope. About half the points fall above the line and half fall below the line. However, it is also not an appropriate line of best fit. It does not follow the trend of the data as the slope is too steep. Here we see an appropriate line of best fit. It has a positive slope, it has about half the points above the line and half below the line, and follows the trend of the data. This is not perfect, it's just an estimate. If you were to draw your own, yours might look a little different from mine. Once we estimate our line of best fit, we can also estimate the equation of that line. Let's start by remembering that to write the equation of a line, we need both the slope and the y-intercept. To find the y-intercept, we're going to estimate where the line crosses the y-axis. It may not always be at 0. This is an estimate, so your estimate might be slightly different from someone else's. What do you think the y-intercept is of this line? I estimate that the y-intercept is about 90. Anything between 85 and 99 would be a good estimate here. We also need to find the slope. Again, we will be estimating. To find the slope, start by identifying 2 points on the line. They don't necessarily have to be the blue points that are included in the data. It could be any point on the line. For example, let's look at the point 24. 24, 600 is a point on the line, but it is not a blue point of data. It should be a point on the line. I also wouldn't want to use the point, for example, that 22.5, 450. That is a blue point, but it is not a point on the line. I chose to use the green points that you see here, the points 0, 90, which is the y-intercept. You can always use the y-intercept as one of your points, and the points 20, 450. Another good point to use here would have been 24, 600, or for example, maybe that's 16.5, 325. Any of those points will work. You just need 2 points that fall on the red line. To find the slope, we use the equation m is equal to the rise over the run, which is y2 minus y1 over x2 minus x1. Our points were 0, 90 and 20, 450. Remember, the 1s and the 2s just indicate our first point and our second point. So this is x1 and y1. This is x2 and y2. Can you take a minute now and calculate the slope of the line between these 2 points? I substituted into the equation. Y2 is 450, y1 is 90, x2 is 20, x1 is 0, 450 minus 90 becomes 360, 20 minus 0 is 20, and 360 divided by 20 becomes 18. This does not have to be a whole number. It might stay as a fraction or a decimal. 18 is fine here, but you won't always get a whole number for this one. So we had a y-intercept of 90 and a slope of 18. We can use the slope-intercept form to write our equation. Remember, the slope-intercept form is y equals mx plus b. What will our equation become here? You should have substituted the 18 next to the x since it's the slope, and the 90 into the constant since it's your y-intercept. So our slope-intercept form becomes y equals 18x plus 90. Once we have an equation, we can use this equation to make predictions beyond the data we collected. For example, we could calculate the sunglasses sales for a temperature of 21 degrees, even though a data point doesn't exist there. That's probably better than us just trying to estimate what that new blue point would be. Although it would be about 21, maybe 490. But my equation will give me a much more accurate point, and we'll talk about that during next class. To estimate the equation of a line of best fit, here is a summary for you to put in your notes. Draw a line through the points that has the correct slope that matches with your correlation, has about half the points above and below the line, and follows the trend of the data. Estimate your y-intercept. Estimate 2 points on the line. One can be the y-intercept. Use those points to calculate the slope, and substitute the slope and the y-intercept into the equation for slope-intercept form. And that's it for estimating linear regression. You also can do this using technology, which we will do later in the semester. Thanks so much, guys, and have a great day.